scientists made a shocking discovery. Hold on to your seats. They found a rock on Mars. Incredible, right? Well, yes, but this particular rock might actually prove life existed there in the past. Headlines scream about clear evidence of life beyond Earth. Honestly, at this point, it feels like every pebble NASA point a camera gets crowned a smoking gun for aliens, and then surprise, it's just another grain of dust or weird chemical trace that turns out to be nothing more than Martian housekeeping. Still, this particular rock does have a twist. Its chemistry could actually point to processes we only ever see when life has been around. Big could though. So, let's scrape off the glitter, fight our way through the hype, and see if this one manages to survive. No pun intended. The new discovery comes from Jezero Crater, a place NASA practically circled on the Martian map with a big red marker billions of years ago. It wasn't a barren pit of dust. It was a lake with a river delta pouring into it. Deltas are nature's filing cabinets. They trap mud, organics, and anything else drifting by. If Mars ever kept a record of ancient life, Jezero is exactly where that record will be stored in mid-2024. Perseverance drilled into a rock in a zone called Bright Angel on the edge of the ancient river valley. The rock got the nickname Caiva Falls. And at first glance, it's just another block of reddish mudstone. But when the rover zoomed in, scientists noticed something unusual. The surface is covered in strange textures, ring-like patterns nicknamed leopard spots. Lighter centers rimmed by darker halos. Scattered among them are tiny nodules that researchers call poppy seeds. These markings are only fractions of a millimeter to a millimeter across, but they are not random stains. They look like chemical reaction fronts frozen in place. And keep in mind, these mudstones date back about 3.2 to 3.8 billion years. So, whatever is recorded in them reaches deep into Mars' early history. The markings are made of minerals like vivianite and iron phosphate and gradite and iron sulfide. Yeah, no idea what those are, but scientists seemed excited. Likely because on Earth, this exact pairing often appears where microbes have been feeding on organic matter and cycling iron and sulfur. Their metabolism changes the chemistry of the environment, leaving behind those ringed halos and nodules. So, this isn't just a random pebble. It's a carefully preserved chemical time capsule from an ancient Martian lake. If you found the same rock on Earth, most geologists would call it biosignature without hesitation. But as always in science, it's not that straightforward, right? We've all been here before. The internet explodes with headlines, life beyond Earth discovered. And for a split second, it feels like we're about to join the Galactic Federation. But once you actually read past the headline, the story tends to shrink. Europa is a perfect example. In 2012, Hubble picked up plumes of water vapor erupting from its frozen surface, a discovery that built on Galileo's earlier hints from the 1990s. Those plumes suggested that beneath Europa's crust of ice lies a vast salty ocean in direct contact with a rocky seafloor. On Earth, when seawater circulates through rock at the bottom of the ocean, it produces hydrogen and other chemicals that microbes can use as an energy source. So life in Europa's ocean, if it exists, could be powered by chemistry created at the seafloor. Suddenly, this Jupiter's moon wasn't just a cold ball of ice. It looked like one of the best places in the solar system to hide life. Then came Venus. In 2020, a research team announced they had found phosphine gas in the planet's thick clouds. On Earth, phosphine shows up almost exclusively because of microbes. Tiny organisms in oxygen-starved places like swamps, sewage, or even the guts of penguins pump it out as part of their metabolism. Outside of biology, you almost never see it. So, when scientists thought they spotted phosphine floating high in Venus's clouds, it sounded like something alive was stirring up there. At least that was the initial excitement. But when you strip away the hype, what we were left with were hints. Plumes in the telescope data, trace molecules in a spectrum. Still exciting, but not hard evidence. These are what scientists call biosignatures. Indirect clues an environment might support life or that something biological could be happening. Yet, even as biosignatures, those discoveries didn't hold up. Europa's geysers, for instance, didn't stand the test of time. The thing is, plumes are notoriously hard to confirm. Later, Hubble observations didn't always see them, leaving open the possibility that the original geysers were just noise in the data. As for Venus's phosphine, follow-up studies revealed that the signal was faint. The data itself is tricky to interpret, and it makes space for alternative explanation from volcanic activity to chemistry we don't yet fully understand. Some teams didn't see phosphine at all when they reanalyzed the same data. Biosignatures are indirect, but the Mars evidence is as solid as a rock cores it is literally a rock. Still, the patterns like the ones we see on it can form in more than one way. You don't have to invoke microbes to explain them. Geology has its own bag of tricks. So, let's go down that list. One candidate is so-called abiotic redox chemistry. Basically, reactions that shuffle electrons around without life being involved. In theory, you could reduce sulfate to sulfide with a bit of organic matter and end up with similar mineral textures. And just to be clear, organic matter doesn't automatically mean alive. It can also be chemical leftovers from non-biological processes. At the low temperatures these rocks record, though, those reactions barely crawl. To run at a useful pace, they normally need 150 to 200 degrees Celsius. But Shovel Falls mudstones are fine-grained and neatly laminated with no signs of being baked. If heat had cooked in those minerals, the rock would look roasted. It doesn't. Another option was acidic fluids washing through and scrambling the chemistry. If the waters had stayed strongly acidic, you'd expect different phosphate minerals to appear, things that only grow in really low pH conditions. But none of those show up here. Instead, the mineralogy is dominated by vivianite and greygeat, minerals that form under moderate pH, low oxygen conditions in standing water. Think calm lake bottom, not acid bath. Put simply, the easy it's just geology explanations don't fit the evidence. And yet, even here, there's a reason to be cautious. It wouldn't be the first time the life on Mars alarm bells rang loud, only to end in disappointment. Back in 1976, NASA sent Viking 1 and Viking 2 to Mars with experiments designed to answer the biggest question directly. Is there life in that soil? The most famous experiment was the labeled release. The setup was straightforward. Scoop up Martian soil, add a nutrient solution tagged with radioactive carbon, and then check if the soil breathes out radioactive carbon dioxide. On Earth, microbes metabolize nutrients and release CO2 as waste. So, if microbes are present in Martian soil, they'll eat the nutrients, digest them, and give off CO2 that carries a radioactive label. And Viking's detectors saw it. The soil responded with a rapid release of gas as if something in it had just eaten lunch and burped. At first glance, it looked like Martian microbes had been caught in the act. But then came the deal breaker. Viking's gas chromatograph mass spectrometer. The instrument meant to sniff out organics, GCMS, works by heating the soil to hundreds of degrees, vaporizing whatever's inside, then sending the vapor through a column that separates molecules by size before a detector weighs them molecule by molecule. That way you can tell if carbon-based organics are present and even identify what types, if the labeled release result really was biology. The GCMS should have been flooded with organic signatures. Instead, it found nothing. It remained a mystery until 2008 when NASA's Phoenix lander dug into Martian soil and found perchlorates chlorine-rich salts that turn into fierce oxidizers when heated. And how did Viking test for organics? By literally baking the soil. That's the worst possible setup if perchlorates are around. Once you crank up the heat, they release oxygen and chlorine that shred any fragile organic molecules into simple gases like carbon dioxide. So, Viking may not have been proving Mars sterile. It may have been destroying the very evidence it was looking for. Talk about first contact. Microbes say hello and we reply with a blowtorch. Now, you'd think that finding perchlorates would make the scientific community jump back to life on Mars confirmed. But nope. Most researchers believe the Viking gas release was just weird Martian chemistry. Reactions with reactive soil, not little microbes hiding in the dirt. And that's the real lesson here. Looking for life on another planet isn't just about pointing a detector and waiting for the microbes to wave. It's a minefield of ambiguous signals, false positives, and instruments that sometimes do more harm than good. So, what now? Do we need an actual chunk of Mars with a life form in it to land on Earth for us to finally be convinced? Well, that already happened. In 1984, scientists trekking through Antarctica picked up a weird greenish-gray rock, later catalogued as Allen Hills 84-001. Tests showed it was blasted off Mars by an impact about 15 million years ago and eventually crash-landed in Antarctic ice some 13,000 years ago. Already cool enough. But in 1996, NASA dropped a bombshell. This meteorite, they said, contained fossilized Martian microbes. The claim was so huge that President Bill Clinton went on live TV to announce it. But what did the rock actually show? Under the microscope, scientists pointed to tiny worm-like structures, magnetite crystals that looked like bacterial byproducts and bits of organic molecules. The story wrote itself. Ancient Mars had life, and some of it had hitchhiked across space in this meteorite, preserved until we found it on Earth. But the closer researchers looked, the shakier it got. The fossils were way too small to be cells as we know them, only about 20 to 100 nanom across, when even the tiniest known bacteria on Earth are closer to 200 nanom. The magnetite crystals could form through regular geological reactions under heat and pressure, and the organic molecules were almost certainly modern contamination from the Antarctic ice. In the end, every one of the biosignatures in ALH 84-001, music, found a perfectly good abiotic explanation. And in Kai Fool's case, we've already ruled out geological reactions and weird chemistry. But what about contamination? Maybe these organics are just space dust that drifted in a molecule smeared onto the rock later. I'm afraid the data don't back it up either. Perseverance's instrument called Sherlock, a laser spectrometer that can scan tiny spots on a rock and pick out organic molecules, found that instead of being scattered randomly, the organics are anchored to the very places the vivianite and grigite minerals formed, the rims of those leopard spots and poppy seeds. The signal even grows stronger in the less oxidized rocks where those minerals are more abundant. In other words, the organics aren't just smeared on the surface. They are built into the rock's own chemical patterns. If it were random space dust, you wouldn't get such a perfect match. It's like throwing a deck of cards in the air and having them fall back into a poker hand. Life just doesn't work this way. In the end, the simplest explanation is this. Billions of years ago, in a Martian lakebed freshly laid with mud, some ancient bacteria started reacting with iron and sulfur in the sediments under low oxygen conditions. That reaction freed up iron, which paired with phosphorus to make vivianite. Sulfur was reduced too, producing gray G. As the chemistry spread outward, it used up its fuel and left behind the rings, nodules, and leopard spot patterns we see today. If we ever want proof beyond a doubt, the next step is getting Martian rock into Earth labs. Samples we can slice, stain, and probe in ways no rover could ever manage. That's why Perseverance isn't just drilling rocks for fun. Each time it bores into a target, it stashes a powdered core into a sealed titanium tube, checks it for contamination, and logs exactly where it came from. Those tubes are then hermetically sealed, stored in the rover's belly, and in some cases dropped onto carefully chosen flat sites on the surface as depot. Think of it as a breadcrumb trail of science capsules. The grand plan, dubbed Mars Sample Return by NASA and ESA, is to fetch those caches, launch them off Mars aboard a small rocket, hand them off to an orbiter, and finally shoot them back to Earth. The idea was to bring those tubes home in the early 2030s, but the budget estimates ballooned to over $10 billion, and by 2024, the program was officially paused. For now, no one can say when we'll actually lay our hands on those samples. But even without them, the evidence Perseverance has already collected is strong enough to keep the case for past life on Mars very much alive. So, we tried to debunk this one. But guess what? We couldn't. And neither can the scientists. For now, the null hypothesis that this isn't life is the one that's failing. After decades of false alarms, we've all become a little too good at rolling our eyes. At this point, actual aliens could stroll past Perseverance, wave a tiny flag, maybe even photobomb a selfie, and would still mutter, "Duh, clickbait." And the truly shocking discovery wouldn't be that life exists on Mars, but that we've grown so suspicious we can't believe it anymore.